Hi folks, welcome to the Math 611B Concept Roundup for sections 3.4 and 3.5. We're looking at kinematics, economic models, rates of change, and trig stuff. You can check the video description below for a review sheet with worked solutions. There's also a downloadable blank copy of the notes, and the video is also time-stamped. So if you're interested in, say, economic models, just go to the time that's listed in the video description. All right, so let's get down to it. Rates of change. We're talking about slope here, and slope measures rate of change. And it's the units that give it meaning. So when we talk about average rate of change, that corresponds to the slope of a secant, which is the change in y over the change in x. And we'd keep the units for those. If we were looking at instantaneous rate of change, well, that's the slope of the tangent, which you could write as f prime of x, or y prime, or better yet, dy by dx. And you can see how similar these two things are. They both talk about y over x. In the instantaneous rate of change, we're just talking about infinitely small changes in y and x. So here's an example. We've got a large tank that's being emptied. The number of gallons remaining in the tank after t minutes is given by this formula. We want to find the average rate of change of the volume in the tank over the first 5 minutes. Okay, well, if I were going to graph this, I might put volume over here in gallons and time in minutes down here on the x-axis. And I would be interested in what happens at 0 minutes. So if I were to put in 0 into this function, I'll have 100 times 0 squared minus 6,000 times 0 plus 90,000. I'll get 90,000. Okay. So there's a point. 0, 90,000. If I'm looking for the volume at 5, well, that'll be 100 times 5 squared minus 6,000 times 5 plus 90,000. And it turns out that that equals 62,500. So I could put that as another point. 62,500 would be over here at 5 minutes. So 62,500. We said average rate of change is the change in y over the change in x. So here, if I want average rate of change, I'd have the change in volume over the change in time. And it's always final minus initial. So 62,500 minus 90,000, all over 5 minus 0. That means nothing unless we put in our units. So that's gallons over minutes. If I were to work that out, that's negative 27,500 gallons per 5 minutes. Or if we divide those things out, you get negative 5,500 gallons per minute. So that's the average rate at which water is leaving the tank. But that rate is not going to be uniform. You can see right from the equation that is quadratic that those things are going to be connected by a curve, by a parabola that's opening upward. So if we want the exact rate of change when time is 5, really we're looking for the slope of the tangent at that point, which is going to be different from what we found. What we found was the slope of the secant. Okay, so we suspect that it'll probably be a slightly lower rate of change. Let's figure out what it is. So we have, for part B, what rate is the water leaving the tank exactly after 5 minutes have passed? Well, we'd find dv by dt, the first derivative. Okay, and looking up here, we've got our equation, so we'd get 200t minus 6,000. If we want to figure out what's happening when t equals 5, then we just sub in 5. So 200 times 5 minus 6,000, that's going to give us negative 5,000. But the dV by dt tells us the units. It's in, dV would be in gallons, and the T would be in minutes. The fact that it's negative means that the amount of water is decreasing. So if we were to interpret this, we'd say at T equals 5 minutes, water is leaving the tank at a rate of 5,000 gallons per minute. And the connection we want to make to the negative is that the negative, right here, tells us that it's leaving. So that's just a general example that lets us know what's going on with a rate of change. Kinematics are a common application. It's the mathematics of motion. So when we see a position function s with respect to time, so it could be anything that models either height or position left or right or forward, backward, then the first derivative, s prime, or ds by dt, means velocity. The second derivative would be in units of time squared, so it would be acceleration. Now we need to be able to decode some of these kinematics questions. So velocity is slightly different than speed. Velocity gives us direction as well. We're only going to be talking about questions that are in one dimension, so they could be either right or left, or upward, downward, or forward, backward. If you have motion to the right, or upward, or forward, typically that's going to mean velocity is positive. Okay? We're moving to the right, or moving up. If we're moving downward, or left, or backward, velocity is negative. If you're at rest, so you're probably watching this video sitting down, your velocity is 0. If you reverse directions, when you reverse directions, your velocity momentarily becomes 0, and then it changes sign. It changes from forward to backward, or up to down, or left to right. And there are tables we can set up to investigate that. If you're moving at a constant velocity, then the acceleration is 0. And speeding up and slowing down have specific definitions. They mean that velocity and acceleration are in the same direction if we're talking about speeding up. So that means either they're both positive or both negative. So if they're both positive, that means that you're speeding up and moving to the right. If they're both negative, then you're speeding up and moving to the left. Slowing down, that means velocity and acceleration are in opposite directions, or have opposite signs. So if velocity is positive, but acceleration is negative, that means you're moving to the right, but you're slowing down. If velocity is negative, but acceleration is positive, well, you're moving to the left, but slowing down. A couple of little notes here. Speed is the absolute value of velocity. So if you're going with a velocity of negative 20 meters per second, that's still a speed of 20 meters per second. Think about your car. It has a speedometer. It only measures how fast you're going, not about the direction. And the third derivative of position is called jerk. Okay, so let's put that to use in a big question here. We've got a particle that moves along a line so that its position at any time greater than or equal to 0 is given by that function, t cubed minus 6t squared plus 9t plus 3, where the position is in centimeters and time's in seconds. So that's kind of a contrived setup, but it's a good way for us to investigate what motion looks like in a function. And we've got a whole bunch of questions here, and we can kind of decode them and figure out what's going on. We'll have to do that bit by bit. So the first thing is find the position when time is 0. That should be pretty straightforward for us. So s at 0 would be 0 cubed minus 6 times 0 squared plus 9 times 0 plus 3. So it starts off at 3. Now 3 what? 3 centimeters, and that's 3 centimeters right of the origin, because it's a positive position. Okay, S at 2, well, same thing here. 2 cubed minus 6 times 2 squared plus 9 times 2 plus 3. That's going to give us a position of 5 centimeters. And we're still talking to the right of the origin. Okay, part B. Find the average velocity over the first 2 seconds. Here, we need to look at the change in position over the change in time. So average velocity equals change in position. S means position over change in time. Okay, and it's always final minus initial, so that would be 5 minus 3 measured in centimeters over 2 minus 0 measured in seconds. Or 2 centimeters in 2 seconds. Its average speed is 1 centimeter per second. But that's not necessarily exactly what's happening when time is 2. Velocity could be changing, and in fact it is changing. If we want the velocity function, well, we just differentiate. It's the first derivative of position. So we'll get 3t squared minus 12t plus 9. If you like, we can factor that. So that would give us t squared minus 4t plus 3. And we could even factor it further. Now, you don't have to, but it will be useful for some of the later stuff that we'll do. So the velocity at 2 comes from just subbing 2 into one of those forms of the equation. Let's do it into the factored form. It would give us 2 minus 3 and 2 minus 1. So 3 times negative 1 times 1 is going to give us negative 3 centimeters per second. What that means is that on average over the first 2 seconds, there was a rightward motion. But right at 2 seconds, it must be moving left. Okay, so there's interesting things about the life of this particle that we can investigate. What time does the particle reverse directions? So in order for it to reverse directions, we need to decode this to mean velocity is 0. Okay, and the velocity function was given by 3t squared minus 12t plus 9, or that factored form, which looked like this. Now, from factored form, you can just see right away the numbers that are going to zero at this function are at t equals 3 and t equals 1. We call these critical values. Okay, once we know that, we can make a sine table. So there's an interval of time from 0 to 1, from 1 to 3, and from 3 to forevermore. And those are the only times where interesting things can happen to the particle, where it could reverse directions. So let's see. If I put in, say, a number between 0 and 1, if I put in 0.5, then velocity is going to be 3 times a negative times a negative. It'll give me a positive, which means that the motion is to the right. If I put in the number 2, I'll end up with 3 times 1 times negative 1. I'll end up with a negative, which means we're moving left. And if I put in 1,000,000, well, I'll get positive, and we'll be moving right again. Okay, so the question is, what time does the particle reverse directions? It changes from rightward motion to leftward motion at t equals 1. And it goes from left to right at t equals 3. Those are the 2 times when this happens. E asks us, what is the position when the particle changes directions? So really, we want to know the position at 1 and the position at 3. If I were to sub those into this position equation up top, I'm going to end up with 7 and 3. And you can just run those through. F, we're going to draw a motion diagram. So here's what we need to know. What's going on with the motion of the particle? The very first question we asked was, what was the initial position? So S at 0 turned out to be 3. So here is where the particle starts, when time equals 0. Now what happens? It moves to the right until time is 1. And when time is 1, it has a position of 7. So I'm going to show that. T equals 1. Now really, we shouldn't be moving upwards. This is only left and right direction. But we need to show somehow the passage of time. Okay, and then when S is 3, well, it moves to the left until S is 3, and it gets to a position of 3. And then what happens? Well, forevermore, if we take a look here, we move to the right. So that's the entire story of the particle. If you wanted to find the distance that it travels over the first 3 seconds, well, it goes 4 centimeters this way, and then another 4 centimeters this way. It must have traveled 8 centimeters. Even though, after 3 centimeters, it's right back where it started. So we could call that its displacement was 0, but its distance that it traveled was 8 centimeters. Okay, we want to make a sine table for acceleration. So here's what we knew. Velocity was 3t squared minus 12t plus 9. This form is going to be more useful for us because we need to differentiate it to find acceleration. Okay, so we had already said that acceleration was the second derivative of position, or the derivative of velocity. If I factor that, I can see the number that zeroes it out. The most important number in here is 2. So that's the number I'm going to make my sine table for acceleration around. If I put in, say, 1 into the acceleration function, I will get a negative. If I put in 3, I'll get a positive. And for every other value greater than 2, I'll get a positive. So the last piece of the puzzle is, when is the particle speeding up? Now, there are a bunch of ways that you can look at this. You can look at the two tables for velocity and acceleration separately and try and figure it out. Or, if you like, you can make one mega table. So it's up to you, but we'll go through the mega table idea here. If you do the mega table, you need intervals of time that go around every critical value. So the first interval from the velocity function was 0 to 1. Okay? Then we'd have an interval that starts at 1, and it has to go to the next critical value. Well, there was a 3 in velocity table, but before that, if we take a look at the acceleration table, there was a 2. So something happens to either velocity or acceleration around 2. Because remember that speeding up and slowing down is the relationship between velocity and acceleration. Okay, if I went to the table, the one that we generated already, we'd have positive velocity, then negative all the way up until 3, and then positive here. If I look at acceleration, well, it starts off negative. It stays negative right up until time is 2. And then after that, it's positive forevermore. So let's think about what's happening here. From 0 to 1, we have positive velocity and negative acceleration. That means it's moving right, but it's slowing down. Then we have negative, negative. That means it's moving left and speeding up because they're the same. Okay, we're looking at whether these two things are the same. Negative, positive, that means slowing down, moving to the left, but slowing down. And finally, positive, positive, that means we're moving to the right and speeding up. Okay, so when are we speeding up? If we actually want to answer the question, that's going on from time is 1 to 2, and when time is greater than 3. Okay, there are other applications in kinematics that involve up-down motion. So I wish I could play this video here, but you can look at the link and check it out. It's a great video with Mason launching his guitar into the air. And its height in meters, and he doesn't mean to, by the way, its height in meters is roughly modeled by this function. So we're going to talk a bit about what we can figure out. The height of the guitar is given by this. So if I put in 2, I'm going to have negative 5 by 2 squared plus 9 times 2 plus 2. That'll give me 0, and it's measured in meters. What does that tell us? The guitar hits the ground, or it's on the ground at t equals 2. Okay, find and interpret the first derivative at t equals 2. So dh by dt would be negative 10t plus 9. And at t equals 2, dh by dt would be negative 10 by 2 plus 9, or negative 11. Now what is it measured in? It's measured in height, which is meters, per time, which is seconds. The negative means it's going downward. So what we now know is when it hits the ground, the guitar is traveling at 11 meters per second downward. Guitar is traveling downward. At 11 meters per second. Or at a rate of 11 meters per second. Okay, find and interpret the second derivative. So that would be this. Well, that's just the derivative of the derivative. What would it be measured in? It would be measured in, and this is why the Leibniz notation is great, in height, which is meters, over time squared, so per second. So this is meters per second squared. That's a measure of acceleration. What we know is the acceleration is downward and constant. So it's constant at 10 meters per second downward. And this was all roughly sort of sketched out, but that is roughly what acceleration due to gravity on planet Earth is. Okay, if we wanted to, we could have made it a little more accurate, but it's about the same. On Earth, it's 9.79. Here, this is 10. When does the guitar reach its maximum height? So what we have to think when it reaches its maximum height, for the briefest instant, velocity at its maximum height is 0. And which function is velocity? The first derivative is velocity. Okay? That we found right here. That's what velocity is. So if we set velocity to be 0, we'll have 0 equals negative 10t plus 9, or 10t equals 9, or t equals 0.9 seconds. The last piece of the puzzle would be finding the maximum height of the guitar, which we could have done by completing the square and finding the vertex of the quadratic to begin with. Or, now that we know that it happens when time is 0.9 seconds, we can just sub it in to the initial formula for the height of the guitar, which was this. Okay, if I put that in, 0.9 squared plus 9 times 0.9 plus 2. I check it out in my calculator, and we're going to get 6.05 meters, or about 18 feet in the air. That does not bode well for the guitar. The next thing we'll take a look at is economic models. So if we have some function that models the cost of producing X items, so the cost in dollars of producing X items is given by some function C, then dC by dx is the rate of change of cost with respect to items produced. In economic circles, that's called the marginal cost. And it's measured in, well, the Leibniz notation tells us, dollars per the X's item. The most important feature of C prime, or the derivative, is that it gives us an estimate of the cost of producing the A plus 1th item, the next item. So if you put in a 5 into C prime, it gives you an estimate of finding the price of the 6th item. Let's put that to use. The cost of producing X microwaves is given by this. And these models are sometimes kind of contrived, but we could put in more complicated numbers and have them match up with reality a little better. This is still going to get the point across. We want to find the cost of producing 11 microwaves. Well, you just put 11 into this function. Plus 15 times 11. Okay. If I work that out on a calculator, apparently it costs $770 to produce 11 microwaves. Find the cost of producing the 11th microwave. Well, to find that, we would need to take the cost of making 11 and subtract the cost of making 10. Okay. And if we were to do that, well, the cost of 11 we know is $770. If I were to put in 10 into that function above, this one, I would get $550. So the 11th microwave costs $220 to produce. The corresponding marginal cost is this. First of all, we need the marginal cost function. So that's just the first derivative. And to estimate the cost of the 11th machine, I do C prime of 10. So what this really gives us is the rate of change of cost, but it should estimate, in a lot of situations, should estimate the the cost of making the next item. Now let's see, what are we going to get? We'll get 300 minus 120 plus 15, or $195. These two things are close, but one is actually easier to figure out than the other. The derivative's easier to work with. Now there are applications of this in optimizing your production numbers. They have to do with comparing marginal cost or marginal revenue to average cost and average revenue. But that's beyond the scope of where we're going to go right now. We'll come back to some economic models later, though. Okay, trig derivatives. So here they are. The derivative of sine x is cos x. Derivative of cos x is negative sine x. Tan x is secant squared. Cotan is negative cosecant squared. Cosecant is negative cosecant x. Cotangent x. And secant x is secant x, tangent x. Okay, so let's put that to use in differentiating y equals root x sine x. First of all, I don't like that radical. Let's write it this way. X to the half sine x. Next thing we need to notice is that this is a product rule question. So u prime would be 1/2 x to the negative 1/2. It's two functions of x multiplied together. V prime, well, that would be the derivative of sine x, which we know is cos x. So if we want dy by dx, that is u prime v plus uv prime, or 1/2 x to the negative 1/2 by sine x. plus x to the half cos x. Now, if we want to make it look a little nicer, we might take a common factor of x to the negative a half out. And that's going to leave us with a half sine x. If I take x to the negative a half out of x to the half, its power will go up. So I get x cos x. This is fine at this stage. We've got all the information. This looks a little bit prettier. Let's try another one. We want to differentiate secant x over x squared. So here we've got the quotient rule we have to watch out for. And we're going to simplify this as much as possible. So its derivative is secant x tan x. The derivative of the bottom would be 2x. So dy by dx is u prime v minus uv prime all over v squared. Let's plug in what we've got. So secant x tan x by x squared minus secant x by 2x. And this is all over x squared squared. Let's clean it up a little bit. We'll have x squared secant x tan x minus 2x secant x all over x squared squared. Okay, now you might notice that on the top we have a common factor. We've got an x that's common. We also have a secant that's common. So let's take that out. We'll have x secant x. That leaves us with x tan x minus 2. On the bottom, if I work it out, I have x to the 4. And this gives us some opportunities for simplification. So if you have an x on the top and an x to the 4 on the bottom, well, that's really an x to the 3 on the bottom. So in nicest form, this is going to look like this. Secant x, x tan x minus 2, all over x cubed. Let's revisit tangents just briefly here. So if I want the equation of a tangent, I need to know two things: point and the slope. To find slope, we're going to need to differentiate. To find the point, I know the x value is 5 pi over 6. The y value is just 4 times the cosine of 5 pi over 6. So we do need to know what the cosine of 5 pi over 6 is. And that's going to be a negative number. And it's going to be negative root 3 over 2. Okay. So the y coordinate is negative 2 root 3. Okay, we can live with that. Now, if we want the slope, we need to find dy by dx, or the derivative. Okay, that's going to give us 4 times negative sine x, or if you prefer, negative 4 sine x. And you can skip straight to that if you like. At x equals 5 pi over 6, we'd have dy by dx equals negative 4 by sine 5 pi over 6, or a half. So we get a slope of negative 2. When we find this dy by dx, that's the slope of the tangent. So our last piece of work involves actually finding the equation. We have y minus y1 equals mx minus x1 as our point slope formula. And we just substitute things in. The slope is negative 2. The x value is 5 pi over 6. So that's going to be negative 2x plus 5 pi over 3. Or y equals negative 2x plus 5 pi over 3. minus 2 root 3. If you were to draw those two using a graphic package, it really would look like the tangent. The last thing we're going to talk about is differentiating efficiently. So we want to look at opportunities to simplify before differentiating. If I look for the derivative in this first one, I'm going to have a mess. I've got a product on top, and then I'll have a quotient rule. But if instead I start thinking about it, well, cotangent, that's going to be cosine over sine. This is all over cosine. That means my y is just cosine over cosine. Oh my gosh, my y is just the number 1, and its derivative is 0. If instead we had have used all that product rule and quotient rule stuff, then it would have been painful. So you want to look for those opportunities. Similarly, over here, if you did this with quotient rule, which you don't need to because there aren't two x's, then it's going to take a little while. But if instead we think of this as y equals 3 x to the negative 3, then we know right away y prime is going to be negative 9 x to the minus 4. And when you have just one term like that, it doesn't save you that much time. But if you have a lot of terms, like in this one, well then we're probably going to want to find some efficient way to deal with this. So let me write this out in a form that's good to differentiate. 4x to the half minus 2x to the negative a half plus 3x to the minus 2. Its derivative then would be 6x squared plus 2x to the negative a half. Okay, the next one, negative 2 times negative a half is 1. So this will be x to the negative 3 over 2. And the last one will be negative 6 x to the negative 3. Otherwise, we'd have to use quotient rule a whole bunch. It's going to be painful. So you want to look for those opportunities. Once again, there is a review sheet with worked solutions in the video description. I hope that you've found this helpful, and I'll see you later.